Hello, this is AP Chemistry, Chapter 10. It's on VSEPR, which stands for Valence Shell Electron Pair Repulsion. Here are the 5 basic shapes. We are only going to cover 3 of the basic shapes: linear, trigonal planar, and tetrahedral. The shape of a molecule is determined by the steric number of the central atom. The steric number is the number of atoms bonded to the central atom of a molecule plus the number of lone pairs attached to the central atom. So for a steric number of 2, with a steric number of 2, that means we have 2 atoms. You can see the X and X bonded to the central atom, which is labeled A. Steric number 3, we can have 2 different scenarios here. We have 3 atoms bonded to the central atom, or 2 atoms bonded and 1 lone pair of electrons right here. And lastly, for a steric number of 4, you have 4 things bonded, or 3 bonded and 1 lone pair, or 2 bonded and 2 lone pairs. This last one is the case of water. So the oxygen in the center and the 2 hydrogens, and the oxygen has 2 lone pairs of electrons around it. Okay, so the shape, the molecular geometry, is determined by how the atoms that are all bonded to the central atom are arranged. So for a steric number of 2, a linear electron geometry, you're going to get a linear molecule. For trigonal planar, if you have 3 bonded atoms, you're going to have a trigonal planar shape. So trigonal meaning 3, planar meaning flat. And then if you have 2 bonded and 1 lone pair, then you're going to have a bent shape. Okay, and the bond angle, so the angle between the bonded sets of atoms, is going to be 180 degrees if the steric number is 2. When we move up to a steric number of 3, we have 3 things to arrange as far apart as possible. So that 360 divided by 3 is going to give us 120 degrees apart. And that's as far apart as you can get them. When you have a lone pair of electrons attached to that central atom, it's extra repulsive. You'll see in a second. So even though this says 120 degrees, the bent shape will actually be slightly less than 120. Okay, and then tetrahedral has 4 atoms bonded to the central atom, and it's going to have a bond angle of 109.5 degrees. If you replace one of those bonded atoms with a lone pair of electrons, you're going to have a slightly smaller bond angle here. My dog had something in her throat, sorry. And last but not least, a bent comes from 2 lone pairs and 2 bonded, and this is going to be the smallest of these 3 angles, of all of these. So it starts with tetrahedral 109.5, trigonal pyramidal is slightly less, usually I believe about 108, and then a bent shape, which is about 107. Okay, but those numbers aren't super important. You just need to know that the lone pair of electrons makes them slightly less than 109.5. Okay, so going over those lone pairs of electrons, they contribute to the geometry. So when we include those lone pairs, they're part of the shape of the molecule, but they're not included in the actual drawing of the molecules. When we are talking about the shape name, trigonal pyramidal, we're talking about the 3 bonded atoms being in this pyramid shape, and we're kind of ignoring the electrons up here, but they are what causes, they're going to repel all of the X green atoms here and push them away. Otherwise, if it was just 3 bonded, we would have trigonal planar. And then this bent shape, these 2 lone pairs are going to repel even more and cause it to be this bent shape. So the lone pairs around the central atom, lone pairs around the central atom have no nucleus or positive charge, so that they are more repulsive than a bonded atom. So these two are going to repel because there are electrons spinning around the X atoms. But these electrons up here are even more repulsive because there is no positive center to them. So they're just up here repelling all of the X's and pushing them away with a greater strength than if this was a bonded atom. The bond angles, the angles between the surrounding atoms and molecules with one or more lone pairs, is smaller than those without lone pairs. Okay, so how do we use all of that to actually predict molecular geometries? There are quite a few steps, but once you get the hang of it, it's not too hard. You count up the valence electrons, you draw a Lewis structure, and you use the Lewis structure to figure out the steric number of the molecule, and then you're going to draw the shape, write the name of that shape, and next time we're going to get to polarity, hybridization, and bond angle. Okay, so let's do some examples. We are going to just focus on the Lewis structure and the shapes for this one, and we will come back and do the bond angle, polarity, and hybridization next time. So we have BeCl2. I know these molecules pretty well, so I'm not going to count up the electrons, but you guys would need to count the number of electrons and make sure beryllium, remember, is one of our exceptions, is happy or stable with 4 electrons around it, so we don't need any double bonds here. So the shape of this, I would have beryllium in the middle with 2 chlorine on each, with 1 fluorine on each side. And so this would be, the molecular geometry would be linear. Okay, and I can also tell that because the steric number of this guy is 2. Okay, here we have a steric number of 3. There are going to be 3 sets of atoms around the central atom, and I know one of them is going to be a double bond because we've looked at nitrate already. And this, remember, technically is 3 resonance structures where that double bond moves around and it's split between the 3. So technically we have 1 1/3, 1 1/3, and 1 1/3 bonds, and I should put brackets, but it's going to be too messy, so I'm not going to do that. And so this would look like N, O, O, and O, and this shape is called trigonal planar. Okay, because there are 3 things around the central atom. This double bond counts as 1 set of electrons. So the steric number of 3 makes a trigonal planar shape. SO2, this one I am going to have to add up. So sulfur is in oxygen's group, meaning it has 6 electrons. So there are 3 times 6, which is 18 total electrons. And I'm going to put them all around. So if I did 8, 12, 14, 16, 18, 20, 22, if I drew all of the electrons around here, I would have used 22. Let me just double check that again. And I'm going to go ahead and do it. So remember, if we just give them all 8, then we know how many double bonds we're actually going to need. So there's 8, 10, there's 8, 10, 12, 14, 16, 18, 20. That's what I thought. I knew I miscounted. So because I'm only 2 electrons over, I know I'm going to need 1 double bond here. So I'm going to come and erase these. And whoops, I did not mean to erase that one. And erase these. Okay, and I'm going to force this oxygen to share its electrons. I need my pen back. Okay, so this oxygen has a double bond. Sorry, it's so messy. There are 4 in between this O and this S on the left. Okay, so that's a double bond. So it's going to look like this. We have an S with a double bond O, single bond, and then we have a lone pair of electrons, which we are going to give them a spot because they are going to push these two oxygen atoms. The lone pair of electrons at the top is going to push them away. Okay, so it's going to have the same about bond angle as up here, except the lone pairs of electrons are slightly more repulsive, so it'll be a little bit less than 120. And that shape is just the shape of the O to the S. It is called bent. Okay, CF4 carbon with 4 fluorines is going to look like this guy. Everybody gets 8 for this one. If we add up the number of valence electrons and how many we are putting, they should be equal. And this is carbon tetrafluoride is what that is. And we're going to draw the carbon in the center, and then it's going to have 4. Now here's the tricky thing is we are trying our best not to make it look like a T shape. So we want to show that the angle here is greater than 90 degrees. And the only way to do that is to have these two be in the plane of the paper, and then we have one that comes out, so we draw it as kind of like it's coming out of the board, and the dotted line, which means it's going back, and then we would have our fluorines on each of these. Those are little F's. Fluorine and fluorine. So that shape is called tetrahedral. When you have a steric number of 4 and no lone pairs of electrons. In H3, you'll see is going to have 8 electrons, and this one has a steric number of 4 because there are 3 bonded and 1 lone pair, but it's like we've removed one of these bonded atoms, so it's going to look like a very similar molecule to the one above in shape, except I have 3 H's, and notice I put the lone pair on the bottom of my Lewis structure, but for continuity, I'm going to put it up top here. Okay, so this lone pair of electrons up top takes up space, and it's going to push the H's away from it, causing it to be a pyramid shape. So this shape is called trigonal because there's 3 bonded, the 3 hydrogens. Trigonal pyramidal. Okay, so that's a trigonal pyramidal shape. And then we're going to remove another bond from a steric number of 4. So we're going to have 2 bonded and 2 lone pairs. And here is water, our classic example of a very polar bent-shaped molecule. That's its Lewis structure. So we have O in the center. We are going to have 2 H's. There's 1. There's 2. And we have 2 lone pairs of electrons around that oxygen, which are very repulsive. They're going to push these hydrogen away from them, and they're pushing away from each other as well. And that shape is also bent. Okay, this one is just here to show you guys that if we put chlorine in the center, so each chlorine and fluorine is going to bring 7 electrons. So I should have 7 times 4, I should have 28 electrons. Chlorine and fluorine cannot make double bonds because they're not on the cons list. So I'm going to give everybody 8. And if I stop there, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and 28 are going to go down here. This is a very strange thing. We have 5 sets of electrons. The steric number is 5. So this is just extra. This will not be on the AP exam or on my exam. But what I want you guys to see is that we will have the fluorines right here, the lone pairs, and we're not going to worry about the rest of this stuff. But you can have more than just 4. Okay. All right. Okay, and I think I got that one wrong. That's why I'm pausing for a sec. Let me delete this guy. It actually, 2, 3, would be a T shape. But that's too much. So you don't need to know that. Okay, so that is it for shapes and the names of those shapes. We're going to look at the polarity and hybridization and bond angle next. All right, have a great day, guys.